Most comets lose dust the way a campfire loses ash, light, thin, and easy for sunlight to push away. But 3i Atlas looks like it's shedding dust fast, and some of that dust isn't acting like ash at all. It's acting like heavier pieces that refuse to drift the way they should, even creating a strange feature that appears to point toward the sun. That's the clue, and if the clue is real, it means we're not just watching a comet tail, we're watching a hidden story about what this object is made of. You're watching a comet that came from beyond our solar system, shedding material in a way that does not match the textbook behavior of comets we have studied for centuries. The dust is there, the sun is there, the physics should be straightforward, and yet when astronomers looked closely at 3i Atlas in recent observations, they saw something that made them pause, a tail structure that appears to point sunward, a cloud of grains that seems heavier, more stubborn than the fine powder we expect from typical comets, and a rate of dust loss that raises questions about what this object is made of and how it is coming apart. This is not a story about speculation, this is a story about an observation that refuses to fit neatly into the box we prepared for it. And that is exactly why it matters, because when nature breaks the pattern, it forces us to look deeper, it asks us to reconsider what we think we know. And in this case, the central clue is not hidden in complex data tables or buried in technical jargon. It is right there in the images, dust that should not behave like dust. Stay with me. In the next minutes, we're going to walk through this mystery step by step, starting with the strangest visual clue of all, a tail that seems to point the wrong way. We're going to explain how sunlight acts as a natural measuring tool, how scientists use the shape and direction of a dust cloud to infer the size of the grains inside it, and why the particles coming off 3i Atlas appear to be larger than what we would expect from a normal comet shedding fine powder into space. You do not need to be an astronomer to understand this. You do not need equations or advanced degrees. You just need to follow the logic of what happens when light hits dust, and what it means when that dust refuses to disappear the way it should. This is a detective story, and the evidence is written in the sky. The question is whether we are reading it correctly. Before we go any further, I want you to do something for me. If this kind of real-world mystery excites you, if you want to see more stories where we unpack the strange behavior of objects from beyond our solar system, hit that like button right now, and drop a comment telling me where you are listening from and what you think this dust clue might mean. Are we looking at a natural process we have never seen up close before? Or is there something about interstellar comets that fundamentally changes the rules? I want to hear your take, and if you are not subscribed yet, do that too. Because this story is not over. 3i Atlas is still active, and every new observation has the potential to either confirm what we think we know or flip it completely. So stay close. This is going to get interesting. Now, let's start with the clue that started it all. The one that made experienced observers stop and say, wait a minute, that does not look right. The sun-facing tail. The feature that should not exist if the dust grains were small and light. The anomaly that turned a routine comet observation into a genuine puzzle. And the reason we're even having this conversation in the first place. Look at a comet in almost any photograph, and you will see a familiar shape. A bright head, and behind it, a tail stretching away from the sun. That tail is not random. It is the direct result of sunlight pushing on tiny dust particles that the comet releases as it heats up. The smaller the grain, the more effectively the light pressure shoves it backward, creating that classic swept-back look. It is physics in action, visible to the naked eye, and it has been understood for more than a century. So when astronomers started analysing 3i Atlas in detail, they expected to see exactly that. A tail pointing away from the sun, trailing behind the comet as it moved through space. And for the most part, that is what they saw. But there was something else, a secondary dust feature that appeared to extend in the opposite direction. Not away from the sun, but toward it. And that is the kind of thing that makes you double-check your images, because at first glance it looks impossible. This phenomenon is called an anti-tail, and it is not entirely unknown in comet science. In fact, new research and reporting on 3i Atlas describe jet-like structures inside this rare, sun-facing feature, which adds another layer to what observers are trying to understand. Under certain viewing conditions, when Earth, the comet and the sun line up in just the right way, you can see what looks like a sunward-pointing tail. But it is not necessarily pointing at the sun. Sometimes it is a perspective effect, and sometimes it can also involve real sunward dust structures and anisotropic activity. The key point is that it does not require new physics. Imagine looking at a flat disk of dust particles from the side. From your angle, the particles in the plane of the comet's orbit can appear to stick out in front of the comet, even though they are not defying physics. They are just sitting in the orbital plane, and you are looking at them edge on. That explanation works beautifully for many comets. Astronomers have observed antitails before, and they understand the geometry involved. But here is where 3i Atlas gets interesting. The sun-facing feature was not just visible for a brief moment when viewing angles were perfect, it was prominent. It persisted in observations taken over an extended period in late-year reports. And the structure of the dust cloud suggested something more than just a perspective trick. It suggested that the grains responsible for that feature were not behaving like the tiny, easily pushed particles that normally create comet tails. Let me explain why that matters. When sunlight hits a dust grain, the force it exerts depends on the grain's size and mass. A tiny grain, something the size of smoke particles or fine sand, feels a strong push relative to its weight. It accelerates quickly away from the sun, joining the classic tail that streams behind the comet. But a larger grain, something heavier and more massive, feels the same sunlight pressure but is less affected by it. It does not get blown away as easily. It lingers closer to the comet's path, and if you are looking at the comet from the right angle, those larger, slower-moving grains can create a dust structure that seems to point sunward. Not because they are moving toward the sun, but because they are not moving away from it fast enough. This is the key insight that turned the antitail from a curiosity into a clue. If the sun-facing feature in 3i Atlas is caused by larger dust grains, then we are not just looking at an optical illusion. We are looking at a natural sorting process. Sunlight is acting like a filter, separating the small grains from the big ones. The small ones get swept backward into the main tail. The big ones stay closer to the orbital plane, creating a structure that looks sunward from our perspective. And that is when the questions start to pile up. Why is 3i Atlas producing so many large grains in the first place? Normal comets shed dust, yes, but the bulk of that dust is fine powder, the kind of material that glows brightly when sunlight scatters off it, creating those spectacular tails we see in long exposure photographs. If 3i Atlas is shedding a significant amount of larger material that does not get blown away as easily, then something unusual is happening in the way this comet is breaking apart. You can feel the tension here. On one hand, the antitail can be explained by well-understood physics. Viewing geometry plus dust dynamics equals a sun-facing feature. On the other hand, the prominence and persistence of that feature suggest that the dust size distribution in 3i Atlas is not typical. And that leads to a bigger question. Is this just a quirk of how this particular comet is shedding material, or is it telling us something deeper about what happens to comets that have been travelling through interstellar space for who knows how long? Here is what we can say with confidence. The sun-facing dust structure in 3i Atlas is real. It has been observed, documented, and analysed. The explanation for why it appears sunward is grounded in solid orbital geometry and radiation pressure physics. But the explanation for why it is so prominent, why the dust grains seem to be larger than usual, is still being worked out. And that is where the story gets more complicated. Because once you start asking why the grains are big, you have to ask where they are coming from, how much material the comet is losing, and whether any of this is truly unusual or just something we have never had the chance to see up close before. The wrong-way tail is not wrong at all. It is just nature showing us something we were not expecting and forcing us to think harder about what we are actually looking at. And the next step in understanding it is to dig into how sunlight itself becomes a measuring tool, and why the behaviour of dust under radiation pressure can tell us more about grain size than almost any other method we have. That is where we're going next. The physics behind the push, and what it reveals about the pieces coming off this comet. Imagine standing in a strong wind holding two objects. In one hand, a feather. In the other, a pebble. You release them both at the same time. The feather is gone in an instant, swept away by the air. The pebble drops almost straight down, barely affected by the breeze. Same wind, same moment, completely different outcomes. That is essentially what happens when sunlight interacts with dust grains around a comet, and it is the reason we can use the shape and behaviour of a comet's tail as a natural experiment in grain size measurement. Sunlight is not just light. It carries momentum. When photons strike a surface, they exert a tiny push. For something as massive as a spacecraft or an asteroid, that push is negligible. But for a microscopic dust grain floating in the vacuum of space, that push is everything. It determines where the grain goes, how fast it moves away from the comet, and whether it ends up in the bright, sweeping tail or stays closer to the comet's orbital path. The key factor is the ratio between the grain's surface area and its mass. A small grain has a lot of surface area relative to its weight. Photons hit that surface and deliver their momentum efficiently, pushing the grain with surprising force. A larger grain, however, has less surface area per unit of mass. It is heavier, bulkier, and harder to move. The sunlight still pushes on it, but the effect is weaker. It is the feather versus the pebble, played out on a microscopic scale across millions of kilometers of space. This is why comet tails have structure. They are not just random clouds of dust. They are sorted by size. The finest grains, the ones that scatter light most effectively and create the brightest visual displays, are blown far away from the comet, creating long, graceful tails that can stretch for millions of kilometers. The larger grains, the ones that are harder to push, lag behind. They stay closer to the comet's path, forming a shorter, fainter trail. And if the grains are large enough, they barely form a visible tail at all. They just drift along near the comet's orbit, almost invisible unless you know where to look. Now apply that logic to 3I Atlas. If the sun-facing dust feature is prominent and persistent, and if the grains responsible for it are not being blown away quickly by radiation pressure, then the simplest reading is that a noticeable fraction of those grains are relatively larger or heavier than typical tail dust. Not large in the sense of boulders or pebbles, but large compared to the typical fine dust that dominates most comet tails. We are talking about particles that are big enough to resist the sunlight push, and that changes everything about how we interpret what this comet is doing. Let me be clear, no one is directly measuring these grains with a microscope. We do not have a spacecraft flying through the dust cloud collecting samples. What we have is observations of how the dust behaves, and from that behavior we can infer size. It is indirect, yes, but it is also remarkably powerful. Because the physics is simple and reliable. Small grains go one way, large grains go another way. And the shape, direction, and brightness of the dust cloud tell you which type of grain you are looking at. This is why the antitail in 3I Atlas is more than just a visual curiosity. It is a measurement tool. By analysing the geometry of that sun-facing feature, researchers can estimate the size range of the grains that are creating it, and some analyses suggest those grains may be larger than what simple, fine powder expectations would predict for many comets, though the exact sizes depend on modelling assumptions. They are not tiny smoke particles, they are more substantial, big enough to stay in the orbital plane, big enough to create a structure that persists over time, and that creates tension. Because large dust grains are not easy to produce, when a comet heats up, ice sublimates, turning directly from solid to gas. That gas flows outward, dragging dust particles with it. But the typical dust that gets dragged along is small. It is the loose material sitting on the surface, the fine powder that accumulated over millions of years. Larger grains require more force to lift. They need stronger outgassing, or they need to be liberated by some other process like surface cracking or the breakup of larger chunks of material. So if 3I Atlas is producing a lot of large grains, that tells us something about the comet's structure or activity level. Maybe the nucleus is more fragile than usual, shedding chunks that break down into large particles as they move away. Maybe the outgassing is uneven, creating jets that are strong enough to lift heavier material. Or maybe the dust itself is different somehow, denser or more cohesive than the dust in solar system comets. We do not know yet. But the clue is there in the tail. The grains appear heavier than the fine dust that dominates many comet tails. Sunlight does not push them as efficiently, and that is less typical, especially in a feature this noticeable. Here is the beautiful part. You do not need to understand the equations to feel the strangeness of this. You just need to trust the logic. Sunlight pushes dust. Small dust moves fast, big dust moves slow. If the dust in 3I Atlas is moving slow, then it is big. And if it is big, then something unusual is happening in the way this comet is shedding material. That is the conclusion you arrive at just by watching how the dust behaves under the one force we can measure reliably, radiation pressure. This is physics doing the work for us. Nature is running the experiment, and we are just interpreting the results. The sun is the test chamber. The dust grains are the subjects, and the shape of the antitail is the readout. It is elegant, simple, and powerful, and it leads directly to the next question. If the grains are big, how big are we talking? What does huge actually mean in this context? And more importantly, what does it tell us about what this comet is made of and how it is coming apart? That is where we are going next. The real meaning behind the word huge, and why it matters more than you might think. When you hear the word huge attached to a comet dust story, your mind probably jumps to rocks. Boulders, chunks of debris tumbling through space. That is a natural reaction, and it is exactly the kind of image that makes headlines. But here is the truth. When scientists talk about huge dust grains coming off 3I Atlas, they are not talking about pebbles or rocks. They are talking about particles that are larger than the typical fine powder that dominates most comet tails. and in the world of cometary dust, that difference is significant. Let me give you some perspective. The dust that creates the brightest, most visible comet tails is incredibly small. We're talking about particles the size of smoke or talcum powder. These grains scatter sunlight efficiently, which is why comet tails glow so brightly in photographs. They are also light enough to be blown away quickly by radiation pressure, which is why the classic comet tail always points away from the sun. That is the baseline. That is what we expect to see. Now imagine grains that are 10 times larger or 100 times larger, still microscopic by everyday standards, but massive compared to the smoke-sized particles that normally dominate. These larger grains do not scatter light as efficiently, so they do not glow as brightly. They are also much harder to push with radiation pressure, which means they stay closer to the comet's orbital path instead of being blown into a long sweeping tail. They are still dust in the technical sense, but they behave very differently from the fine powder we are used to seeing. This is what researchers are inferring when they analyze the sun-facing dust feature in 3I Atlas. The grains responsible for that structure are not smoke-sized. They are larger. How much larger is still being worked out because these measurements are indirect and depend on modeling how radiation pressure interacts with particles of different sizes. But the key point is this. The fact that the antitail is so prominent and persistent suggests 3I Atlas may be producing a noticeable amount of dust in a coarser than usual range, at least compared with the finest, sunlight-swept grains that dominate many classic tails. And that raises an immediate question. Why? Why would this comet be producing larger grains? There are a few possibilities, and they all point to something unusual about how 3I Atlas is coming apart. One option is that the nucleus is more fragile than usual. Instead of shedding fine dust as ice sublimates, the comet might be breaking apart in larger chunks, which then fragment into oversized grains as they move away. Another option is that the dust itself is more cohesive or dense, so when it gets lifted off the surface, it does not immediately break down into fine powder. A third possibility is that the outgassing jets on 3I Atlas are strong and uneven, powerful enough to lift material that would normally stay stuck to the surface. Any of these explanations could be true, and they are not mutually exclusive. But they all have one thing in common. They suggest that 3I Atlas is not behaving like a typical solar system comet, and that is exactly what makes this story compelling. Because this is an interstellar object. It formed somewhere else in some other star system, and it has been travelling through the galaxy for who knows how long before wandering into our neighbourhood. If its dust properties are different, if the way it sheds material is unusual, then that difference might be telling us something about where it came from and what it experienced on its journey. Here is where I need to be careful. The inference that the grains are large is based on observations and modelling. It is not based on direct imaging of the grains themselves. We do not have close-up photos of individual particles. We do not have samples we can analyse in a lab. What we have is the behaviour of the dust cloud, and from that behaviour, we can work backward to estimate grain sizes. This is standard practice in cometary science, and it is a reliable method, but it is also subject to uncertainty. Different models, different assumptions about grain density and composition can lead to different size estimates. So when you see claims about huge dust grains, keep that context in mind. The grains are larger than typical comet dust, that much is clear, but the exact size distribution is still being refined, and the word huge is relative. It means big compared to the fine powder that normally dominates, not big in the sense of rocks or pebbles. This is an important distinction, because it separates what we can confidently say from what is still under investigation. The reason this matters is simple. If 3I Atlas is shedding large grains, then it is also shedding a lot of mass. Large grains carry more material than fine dust. They represent a more significant loss of material from the comet's nucleus. And that leads to the next layer of the mystery. How much dust is this comet actually losing? How do we estimate that from what we can see? And what does the answer tell us about the long-term fate of this object? Because if 3I Atlas is shedding material at a higher than typical rate in some models, then it is changing as we watch it. It is not a static object. It is evolving, breaking apart, possibly even fragmenting. And that makes every new observation more valuable, because we might be watching a process that we have never had the chance to see up close before. The word huge is a clue. It is shorthand for larger than expected. And in science, larger than expected is always a signal that something interesting is happening. It means the model you had in your head does not quite fit the data. It means you need to dig deeper, ask more questions, and be willing to update your understanding when the evidence demands it. That is what we are doing here. We are following the clues, one step at a time, from the shape of the tail to the size of the grains, and from the size of the grains to the question of mass. How much material is coming off this comet, and what does that tell us about what is happening at the nucleus? That is the next piece of the puzzle. Imagine watching someone empty a bucket. But you cannot see inside the bucket. You can only see the water flowing out and the puddle forming on the ground. From that you have to estimate how much water was in the bucket to begin with. That is essentially what astronomers do when they try to measure how much dust a comet is losing. They cannot see the nucleus directly, they cannot weigh the material being shed, but they can observe the dust cloud, measure its brightness, analyze its structure, and from that, build an estimate of how much mass is leaving the comet. This is where the story of 3I Atlas shifts from grain size to grain quantity. Because it is one thing to say the comet is shedding large particles, it is another thing entirely to ask how many large particles it is shedding, and whether that amount is unusual compared to other comets. And here is where the observations get even more interesting, because the answer seems to be yes. The amount of dust coming off 3I Atlas appears to be significant, more than what you might expect from a small inactive object that has been wandering through interstellar space for millions of years. Let me walk you through the logic. When dust scatters sunlight, it creates a glow. The brightness of that glow depends on two things: the number of grains and the size of the grains. If you have a lot of small grains, you get a bright, widely distributed glow. If you have fewer but larger grains, the glow is fainter but more concentrated. By measuring the brightness of the dust cloud at different wavelengths and analyzing how it changes over time, researchers can estimate the total mass of dust in the cloud. It is not a perfect measurement. There are uncertainties in grain composition, density, and how efficiently different-sized grains scatter light, but it is a solid starting point. When researchers applied these kinds of models to 3I Atlas, the results sparked debate. The dust mass estimates suggested that the comet was losing a substantial amount of material, not just a light dusting of fine powder, but a continuous outflow of grains that added up to real mass loss over time. And remember, we are talking about a comet that likely formed in another star system, travelled through the cold, empty void of interstellar space, and then suddenly found itself heating up as it approached our Sun. That heating should trigger outgassing, yes. But the question is whether the amount of outgassing and dust production we are seeing is normal, or whether it is unusually intense. Here is why that matters. Comets lose mass every time they pass close to the Sun. Ice sublimates, gas flows outward, and dust gets dragged along. But there is a limit to how much material a comet can lose before it starts to run out. Small comets, or comets that have been through many close approaches to the Sun, eventually become inactive. They stop producing dust and gas because they have used up their volatile ices. They become dormant, essentially turning into asteroids. So when you see a comet that is actively shedding a lot of dust, especially an interstellar comet that we have never observed before, you have to ask how long that activity can be sustained. If 3I Atlas is losing mass at a high rate, then one of two things is happening. Either it is a large object with plenty of volatile material to spare, or it is a smaller object that is shedding material faster than it can sustain over the long term. And here is where the observations get tricky. We do not have a direct measurement of the nucleus size. We can estimate it based on brightness and assumptions about surface reflectivity, but those estimates have uncertainty. So we are left with a puzzle. A comet that seems to be shedding a lot of dust, possibly including larger grains that represent more mass per particle. But we do not know exactly how big the comet is, or how much material it has left to shed. This creates tension in the story. On one hand, the dust production could be entirely normal. Maybe 3I Atlas is just a typical comet that happens to be very active during this pass through the inner solar system, and the large grains are a quirk of how the nucleus is structured, or how the outgassing jets are behaving. On the other hand, the dust production could be a sign that something unusual is happening. Maybe the comet is fragmenting. Maybe the nucleus is more fragile than expected, and it is breaking apart faster than a typical solar system comet would. Or maybe, as some researchers have suggested, the interstellar journey itself changed the comet in some way, altering its structure or composition so that it behaves differently when it finally gets close to a star. Here is what we can say with confidence. The dust mass estimates for 3I Atlas are model-based. They depend on assumptions about grain size, density, and scattering efficiency. Different models can give different answers. Across multiple discussions of the observations, one theme keeps showing up. 3. The Atlas appears notably dusty, and the sun-facing structure suggests part of that dust may be relatively coarse, but the exact production rate remains model-dependent. More than what you might expect from a faint, distant object that looks relatively small in telescopes. And that is interesting because it suggests that appearances can be deceiving. A comet that looks modest in brightness might actually be shedding a significant amount of material if the grains are large and do not scatter light as efficiently. This is the second clue stacking on top of the first. We have large grains inferred from the antitail structure, and we have substantial dust mass, inferred from brightness and cloud structure. Together, those two clues paint a picture of a comet that is more active and possibly more fragile than you might guess from a casual glance at the images. And that raises the next obvious question. Where is all this dust coming from? What physical processes inside the comet or on its surface could explain both the size and the quantity of the grains being shed? That question leads us directly into the realm of mechanism. What could cause a comet to behave like this? Are there natural explanations that fit the observations, or do we need to invoke something more exotic? And how do we separate what we can prove from what is still speculation? That is the territory we are about to enter, the hunt for the cause, and the challenge of building a story that fits the evidence without overclaiming what we actually know. Because this is where the science gets most interesting, and also most contentious. And it is where we have to be most careful about separating observation from interpretation. When something unusual happens in astronomy, the first instinct is to reach for extraordinary explanations. But the truth is, nature has a deep repertoire of ordinary mechanisms that can create extraordinary-looking results. And before we jump to anything exotic, we owe it to ourselves to walk through the most likely natural explanations for why 3I Atlas is shedding large dust grains at a high rate, because if we can explain the observations with well-understood physics, then we should. That is how science works. You exhaust the simple explanations first, and only then do you start considering more speculative ideas. So let's start with the basics. What makes a comet shed large grains? The most straightforward answer is uneven outgassing. When a comet heats up, ice sublimates on the surface, turning directly into gas. That gas flows outward, and as it does, it drags dust particles with it. But not all parts of the nucleus heat up evenly. Some areas get more sunlight than others. Some areas have more volatile ices just below the surface, and some areas might have a crust or a layer of non-volatile material that insulates the ice underneath, only breaking open when the pressure from sublimation builds up enough. This creates jets, localized streams of gas and dust shooting out from active areas on the nucleus. Jets are common on comets. We have seen them up close on missions like Rosetta, which spent 2 years orbiting Comet Churyumov-Gerasimenko and watched jets turn on and off as the comet rotated and different areas faced the sun. And here is the key point. Jets can be powerful. They can lift larger particles than the gentle diffuse outgassing that happens across the rest of the surface. If 3I Atlas has strong jets, and if those jets are hitting areas where the surface material is fragmented or loosely packed, then it is entirely plausible that the comet could be shedding larger than average dust grains. Add rotation to the mix and things get even more interesting. Comets spin. As they spin, different parts of the surface move in and out of sunlight. Active areas heat up, jets turn on, then those areas rotate into shadow and the jets shut off. This creates a pulsing, intermittent pattern of dust release. And depending on the rotation rate and the location of the active areas, this can create complex dust structures in the coma and tail. Some of those structures can look like they are pointing sunward when viewed from certain angles, especially if the dust being released includes larger grains that do not get blown away immediately by radiation pressure. This is not speculation. This is observed behavior from comets we have studied for decades. The antitail phenomenon itself has been explained in peer-reviewed research as a natural consequence of viewing geometry combined with dust particle dynamics. When you look at a comet from a specific angle, and when the dust includes a range of grain sizes, you can see structures that appear to point in multiple directions. The small grains form the classic backward-pointing tail. The larger grains form a flatter, more planar structure that can appear sunward if you are looking at it edge-on. It is all about perspective and particle sorting. So applying this to 3I Atlas, the simplest explanation is this. The comet has active regions that are shedding dust through jets. Those jets are strong enough, or the surface material is fragile enough, that larger grains are being lifted along with the fine dust. The comet is rotating, so the jets turn on and off, creating a time-varying dust release pattern. And when we observe the comet from Earth, the combination of viewing angle, grain size distribution, and orbital geometry creates a prominent sun-facing dust feature that persists over time. No exotic physics required. Just standard cometary behavior playing out in a way that happens to look unusual from our vantage point. But there is another layer to consider: composition and density. Not all cometary dust is the same. Some dust grains are fluffy aggregates of tiny particles loosely stuck together. Others are more compact, denser, maybe even partially sintered by heat or radiation exposure. The density of the grains affects how they respond to radiation pressure. A fluffy grain has more surface area per unit mass, so it gets pushed more effectively. A dense grain has less surface area per unit mass, so it stays closer to the comet. If the dust coming off 3I Atlas is denser than typical solar system comet dust, that could explain why the grains are harder to blow away and why they create a more prominent antitail structure. And here is where the interstellar origin becomes relevant in a completely natural way. This comet formed in a different star system. It likely formed from a different protoplanetary disk, with a different mix of elements and compounds. It then spent millions or billions of years travelling through interstellar space, exposed to cosmic rays, bombarded by high-energy particles, and slowly altered by radiation processing. All of that could affect the structure and composition of the dust grains locked inside the nucleus. It could make the dust denser, more cohesive, or chemically different from what we see in comets that have lived their entire lives in our solar system. None of this is proven yet, but it is plausible, and more importantly, it is testable. If researchers can measure the composition of the dust using spectroscopy, or if future observations reveal how the dust production changes as the comet moves through its orbit, we can start to narrow down which of these mechanisms is most important. Maybe it is jets, maybe it is rotation, maybe it is dense grains, maybe it is all three working together. The point is, there are multiple natural explanations that fit the observations, and we do not need to reach for anything exotic to make sense of what we are seeing. But here is the reality. In science, and especially in astronomy, not everyone agrees on the interpretation. Even when the observations are clear, even when the natural explanations are plausible, there is always room for debate about whether those explanations are sufficient or whether something more unusual is happening. And in the case of 3I Atlas, that debate has been amplified by some high-profile voices arguing that the dust behavior is more anomalous than mainstream explanations suggest. This is where the story enters more contentious territory. Because there are researchers, including some well-known figures, who have looked at the same data and reached a different conclusion. They argue that the dust mass, the grain sizes, and the persistence of the sun-facing feature are harder to explain with standard cometary physics than most astronomers are willing to admit, and they have suggested carefully but publicly that 3I Atlas might be doing something that pushes the boundaries of what we consider normal for a comet. That is the controversial angle, and it is worth exploring, not because it is necessarily correct, but because it highlights the challenge of interpreting data when you only get one chance to observe an object like this. Interstellar visitors do not come around often. We do not have the luxury of waiting for the comet to make another pass so we can refine our measurements. We get one shot, and we have to make the most of it, which means acknowledging both the mainstream explanations and the alternative interpretations, and being honest about where the evidence is strong and where it is still uncertain. That is what we're going to do next. Walk through the controversial claims, examine what they are based on, and figure out how to think about them without losing sight of what we actually know. There is a name that shows up in almost every discussion of unusual interstellar objects, and that name is Avi Loeb. He is a respected astrophysicist, a professor at Harvard, and someone who has built a career on asking bold questions about what we might be missing when we observe the cosmos. He is also controversial, because he is willing to entertain explanations that most scientists consider speculative, and he does so publicly, in ways that generate headlines and intense debate. When it comes to 3I Atlas, Loeb has made it clear that he thinks the dust behavior deserves more scrutiny than it has received. Let me be very clear about what I am doing here. I am not presenting Loeb's arguments as facts. I am presenting them as claims, as one interpretation of the data, advanced by a credible researcher, but one that is not widely accepted by the broader scientific community. This distinction matters, because in the age of social media and viral headlines, it is easy for a provocative hypothesis to get amplified into something that sounds like settled science, and that does not serve anyone well. So I am going to lay out what Loeb and others have argued, explain why they think it is significant, and then talk about why many other scientists disagree. Loeb's central point is this. When you look at the dust mass estimates and the inferred grain sizes coming off 3I Atlas, the numbers are, in his view, harder to reconcile with natural cometary activity than the mainstream narrative suggests. He points to the fact that the antitail is unusually prominent, that the dust production appears to be sustained over time, and that the grains seem to be larger than what you would expect from typical sublimation-driven outgassing. He has suggested carefully but publicly that this pattern raises questions about whether we are looking at a purely natural process or whether there is something about this object that does not fit the Comet model as neatly as we would like. Now, Loeb has a history of pushing this kind of boundary. He made similar arguments about Oumuamua, the first confirmed interstellar object detected passing through our solar system. Oumuamua was strange in several ways. It accelerated slightly as it moved away from the Sun, but it did not show any visible signs of outgassing that would explain that acceleration. It had an elongated shape, or at least that is what the light curve suggested, and it was brighter than you would expect if it were just a dark, rocky asteroid. Loeb argued that those anomalies could be explained if Oumuamua was not entirely natural, if it had some artificial component, or if it was a piece of debris from a manufactured object. He was careful to frame it as a hypothesis worth investigating, but the media ran with it, and suddenly Oumuamua became the alien spacecraft story. The scientific community pushed back hard. Most astronomers argued, and continue to argue, that Oumuamua's behaviour can be explained with natural mechanisms. Maybe it was outgassing hydrogen, which is hard to detect but could account for the acceleration. Maybe its shape was not as extreme as the initial light curve suggested. Maybe its brightness was due to an icy surface that reflected more light than expected. These explanations are not perfect, but they are plausible, and they do not require invoking anything beyond known physics. The same dynamic is playing out with 3I Atlas. Loeb looks at the dust data and sees anomalies. He sees numbers that, to him, suggest the comet is behaving in ways that stretch the boundaries of what we consider typical, and he raises the possibility, not as a claim of fact, but as a question worth asking, that maybe we are missing something. Maybe there is a mechanism we have not considered. Maybe the interstellar origin matters more than we think. Or maybe, and this is where things get most controversial, there is something about this object that we are not fully understanding because we are too committed to the natural comet explanation. Here is the problem. When you frame an observation as an anomaly, you are making a judgment call about what counts as normal. A normal is a moving target. We have only studied a handful of interstellar objects up close. We do not have a large sample size to draw from. So when Loeb says the dust behaviour is anomalous, what he really means is that it does not fit his expectations based on solar system comets. But solar system comets are not the perfect comparison. They formed here. They have been shaped by millions of years of exposure to our Sun. An interstellar comet might just behave differently, not because it is artificial or exotic, but because it came from a different environment and has a different history. Most scientists who study comets professionally look at the 3I Atlas data and see something interesting but not inexplicable. They see a comet with strong, uneven outgassing, possibly a fragile nucleus, possibly a different dust composition than what we're used to. They see natural mechanisms that can produce large grains and prominent antitails. They see uncertainties in the measurements, yes, but not anything that requires abandoning the standard comet model, and they argue, quite reasonably, that before you invoke something exotic, you need to exhaust the ordinary explanations first. So where does that leave us? It leaves us in a place where the observations are real, the interpretations are contested, and the truth is probably somewhere in the messy middle. 3I Atlas is doing something that looks unusual, but unusual does not mean impossible. It does not mean artificial. It does not even mean unprecedented, because we have only been observing comets with modern instruments for a few decades. And we have only been observing interstellar comets for a few years. We are still building the database of what counts as normal behaviour. The controversial angle is worth acknowledging because it is part of the story. It is part of how science works in real time, when the data is incomplete and the stakes are high. But it is also worth keeping in perspective. Claims are not conclusions. Hypotheses are not facts. And when a single researcher, no matter how credible, makes an argument that most of their peers do not accept, that is a signal to be cautious. Not dismissive, but cautious. Listen to the argument, evaluate the evidence, and recognize that the most likely explanation is often the one that does not make headlines. The next step is to take stock of what we do not know, because that is where the real mystery lies. Not in the speculative claims about exotic behaviour, but in the honest gaps in our understanding. The questions we cannot answer yet, not because the data is pointing to something impossible, but because we simply have not had the chance to measure the things we need to measure. That is the territory we are moving into next. The known unknowns, the missing pieces, the things that, if we could measure them, would settle the debate once and for all, and the reason we might never get those measurements unless we get very lucky or very deliberate about how we study the next interstellar visitor. Here is the uncomfortable truth about 3I Atlas. We are watching it from a distance with limited tools for a limited time, and then it is gone. We do not get to send a probe. We do not get to collect samples. We do not get a second pass to refine our measurements. We get one chance, and when it is over, we are left with whatever data we manage to capture and a long list of questions that we will probably never be able to answer with certainty. That is the reality of studying interstellar objects. They are fleeting, they are distant, and they leave behind more mysteries than solutions. So let's talk about what we do not know. Let's be honest about the gaps in our understanding, because those gaps are where the real science lives. Not in the claims or the speculation, but in the careful acknowledgement of what we have measured, what we have inferred, and what is still completely uncertain. Because that is how you build trust. You admit what you do not know, you show the boundaries of your knowledge. And you make it clear that science is not about having all the answers. It is about asking the right questions and being willing to say, we do not know yet, but here is what we are trying to figure out. First, the grain size distribution. We have inferred that the dust coming off 3I Atlas includes larger than typical grains, but we do not have a precise measurement of the size range. Are we talking about grains that are twice as large as normal dust, 10 times larger, 100 times? And what is the mix? Is the comet shedding mostly large grains, or is it shedding a wide range of sizes with a larger proportion of big grains than usual? These are important questions because the answers would tell us a lot about the physical processes at work on the nucleus. But right now, we are relying on models that have assumptions baked in, and different assumptions lead to different answers. Second, the dust production rate over time. We have snapshots of the comet's activity at specific moments, but we do not have a continuous record of how the dust output has changed as the comet moved through its orbit. Is the dust production steady, or does it vary? Are there periods of intense activity followed by quieter phases? Does the comet brighten and fade as different parts of the nucleus rotate into sunlight, or is the activity more or less constant? These questions matter because they tell us about the structure of the nucleus and the distribution of volatile ices on the surface. But without continuous monitoring, we are left guessing. Third, the nucleus itself. We do not have a direct image of the nucleus. We do not know its exact size, its shape, or its composition. We can estimate size based on how much sunlight the comet reflects, but those estimates depend on assumptions about surface reflectivity, and we do not know if the surface is dark like most comets or brighter. We do not know if the nucleus is a single solid object or a loosely bound collection of smaller pieces held together by weak gravity. We do not know if it is spinning fast or slow, or if it is tumbling chaotically. All of those details would help us understand why the comet is behaving the way it is. But we do not have them. Fourth, the dust composition. We can measure some properties of the dust using spectroscopy, looking at how it absorbs and emits light at different wavelengths. But those measurements are limited by the brightness of the comet and the sensitivity of our instruments. We do not have a detailed chemical inventory of the dust grains. We do not know if they are made of silicates, organics, ices, or some mix of all three. We do not know if the grains are pure or contaminated with other materials, and we do not know if the composition is the same across all the dust being shed, or if different jets are releasing different types of material. That information would be incredibly valuable, because it would tell us about the formation environment of the comet and how it has been altered over time. But right now, we only have hints. Fifth, and this is a big one, the history of the comet. Where did it come from? What kind of star system did it form in? How long did it spend in interstellar space? Did it pass through any dense molecular clouds or other environments that might have altered its surface or interior? These are questions we cannot answer just by looking at the comet. We would need to know its trajectory in reverse, trace it back through the galaxy, and figure out where it originated. That is possible in principle, but it requires precise measurements of the comet's velocity and trajectory, and even then the uncertainties pile up quickly. We might be able to narrow it down to a region of the galaxy, but pinpointing a specific star system is probably out of reach. And finally, the most frustrating unknown. How representative is 3I Atlas of interstellar comets in general? Is this normal behavior for a comet that formed in another star system, or is this comet an outlier even among interstellar objects? We do not know, because we have only studied a tiny handful of confirmed interstellar visitors: Oumuamua, 2I, Borisov, and now 3I Atlas. That is not a large enough sample to draw broad conclusions. It is entirely possible that interstellar comets are highly diverse, shaped by the different conditions in the star systems where they formed and the different journeys they took to get here. Or it is possible that they are all roughly similar, and the variations we see are just noise. We do not know yet. These are the gaps. These are the things we wish we could measure but cannot, given the tools and time we have. And here is the key point. None of these gaps prove anything unusual is happening. They are just gaps. They are the normal limits of observation and inference when you are trying to study something that is millions of kilometers away, moving fast and not cooperating by slowing down so you can get a better look. This is what astronomy looks like in real time. You make the best measurements you can, you build models based on those measurements, you acknowledge the uncertainties, and you wait for the next object to come along, hoping you will have better tools and better luck next time. But here is the other side of that. The gaps also mean that the mystery is not fully solved. The observations are real, the dust behavior is unusual enough to warrant attention, and the questions about grain size, production rate, and composition are not trivial. They are the kinds of questions that, if answered, could change how we think about comets, about interstellar objects, and about the diversity of planetary systems across the galaxy. So the mystery is not a failure, it is an invitation. It is nature handing us a puzzle and saying, figure this out if you can, and even if we cannot solve it completely with 3i Atlas, we can learn enough to be better prepared for the next visitor. We can refine our models, improve our instruments, and ask sharper questions. That is progress, even if it does not feel like closure. So where does that leave us? It leaves us with a comet that is strange enough to be interesting, but not so strange that we need to abandon everything we know about how comets work. It leaves us with observations that challenge our assumptions, but not in a way that breaks the laws of physics. And it leaves us with a long list of questions that we might never fully answer, but that we can use to guide the next generation of observations and missions. That is the honest mystery. Not a conspiracy, not a cover-up, not a sign of something impossible. Just the normal, frustrating, beautiful process of trying to understand something new. And that brings us to the final step, the payoff. What all of this means, why it matters, and what we should take away from the story of 3i Atlas and its stubborn, sunward-pointing dust. You made it. You followed the clues from the wrong-way tail to the size of the grains, from the sunlight push to the mass budget, from the natural explanations to the controversial interpretations, and through the honest gaps in what we still do not know. And now we are here. The final piece. The question that ties it all together. What does this mean? Not just for astronomers or astrophysicists, but for anyone who cares about understanding the universe we live in and the strange, beautiful objects that wander through it. Let me start with the simplest answer. 3i Atlas is a reminder that nature is more interesting than we give it credit for. We spend so much time building models, refining theories, and trying to predict what we will see next, that when something does not quite fit the mold, it feels like a challenge. But it is not a challenge to the validity of science. It is a challenge to our assumptions. It is nature saying, you thought you had this figured out, but there is more to learn. And that is exciting. That is what drives discovery. The dust behavior in 3i Atlas is unusual, yes, but unusual does not mean impossible. It means we are seeing something we have not had the chance to study up close before, an interstellar comet formed in another star system shaped by a different history, shedding material in ways that reveal details about its structure and composition. The fact that the dust includes larger grains, the fact that the antitail is prominent, the fact that the dust production is sustained over time, all of that is real. And all of it is telling us something about what happens when a comet that has been travelling through the cold void for millions of years suddenly finds itself close to a star again. Here is what makes this story powerful. We did not need a spacecraft to make these discoveries. We did not need a billion-dollar mission to fly out to the comet and take close-up photos. We used telescopes here on Earth, looking up at a faint, distant object, and we let physics do the work for us. We used sunlight as a natural measuring tool, pushing on dust grains and sorting them by size. We used radiation pressure as a filter, separating the small grains from the large ones and revealing the hidden structure of the dust cloud. We used geometry, orbital mechanics, and the simple fact that dust scatters light to build a picture of what this comet is doing. That is elegant. That is the beauty of astronomy. You let nature run the experiment and you just watch and interpret. And what we learned is that 3i Atlas is not a simple object. It is not a dead rock tumbling through space. It is active. It is shedding material. It is changing as we watch it. And the details of how it is shedding material are different enough from typical solar system comets that it raises questions about where it came from and what it experienced on its journey. Those questions might never be fully answered, at least not with this comet. But they set the stage for the next interstellar visitor. They give us a framework for what to look for, what to measure, and how to interpret the data when we get it. There is also a deeper lesson here, and it is about how we handle uncertainty. Science is not about proving things with absolute certainty. It is about building the best explanation we can based on the evidence we have, and then being willing to update that explanation when new evidence comes in. The story of 3i Atlas is messy. The data is incomplete, the models have uncertainties, the interpretations are contested, and that is okay. That is how real science works. It is not a finished product, it is a process. And the process involves arguing, testing, revising, and sometimes admitting that we do not know yet. What we do know is this. 3 Atlas is shedding dust at a noticeable rate. The dust includes grains that are larger than the typical fine powder that dominates most comet tails. The sun-facing dust feature is prominent and persistent, and it can be explained by a combination of viewing geometry and dust grain dynamics. The most likely explanations involve natural processes like uneven outgassing, rotation, and differences in dust composition or density. But there are still open questions about the exact grain size distribution, the dust production rate over time, and the structure and composition of the nucleus. And those questions matter because they are the key to understanding how interstellar comets behave and what makes them different from the comets we're used to seeing. So here is the payoff. You now know more about this comet than most people who saw a headline about it. You understand the clue, the physics behind it, the natural explanations, and the limits of what we can say with confidence. You can see the difference between observation and interpretation, between data and speculation, between what is proven and what is still under debate. And you can take that framework and apply it to the next strange object that shows up in the news. Because there will be more. Interstellar visitors are rare, but they are not impossible. We have detected 3 so far, and as our telescopes get better and our surveys get more comprehensive, we are going to find more. And when we do, the lessons from 3I Atlas will matter. We will know to look for antitails and dust structures that reveal grain sizes. We will know to measure dust production rates and compare them to models of cometary activity. We will know to separate what we can observe from what we have to infer, and to be honest about the uncertainties. We will know to consider natural explanations first, and to be skeptical of claims that sound extraordinary, without extraordinary evidence to back them up. That is the legacy of this comet. Not a solved mystery, but a better understanding of how to approach the mystery. I want to leave you with one final thought. The universe is full of things we do not understand yet, and that is not a problem. That is the point. If we understood everything, there would be nothing left to discover. The fact that 3I Atlas is strange, the fact that it raises questions we cannot fully answer, the fact that it challenges our assumptions and forces us to think harder, that is what makes it valuable. That is what makes it worth talking about. Because every mystery solved leads to 10 new mysteries, and every question answered opens the door to 100 new questions. So here is what I want you to do. Drop a comment right now and tell me what you think. What is the most convincing explanation for the dust behavior in 3I Atlas? Is it natural outgassing and rotation? Is it a fragile nucleus breaking apart? Is it something about the dust composition that makes it denser or harder to push? Or do you think there is something we are missing, some mechanism we have not considered? I want to hear your take, and if you are not already subscribed, hit that button, because this story is not over. 3I Atlas is still being observed. New data is still coming in, and if something changes, if we get a new measurement that shifts the interpretation, you will hear about it here first. This is the kind of story that reminds you why space exploration matters. Not because we are looking for aliens or hunting for the next big sensational headline, but because we are trying to understand our place in a universe that is bigger, stranger, and more beautiful than we ever imagined. And every new visitor from the stars is a gift, a chance to learn something we did not know, a chance to test our theories against reality, a chance to be humbled by how much we still have to figure out. 3. Atlas is shedding dust fast, and the pieces are huge. That is the observation. The physics is real. The mystery is honest. And the journey to understanding it is exactly what science is supposed to be. Messy, uncertain, contentious, and absolutely worth the effort. Thanks for sticking with me through this. Now go think about it, talk about it, question it, and keep looking up because the next interstellar visitor could show up any day, and when it does, we will be ready.